Right, it's 4 o'clock. Let's go and get started. Good afternoon, everyone. How's everyone doing today? Good, doing good. Okay. All right. So it's our second lecture this week. So second lecture of week 5. So we're starting something new today, and so we're pretty much done with all the classical methods, and so we've gone over single variable, multivariable, quality, inequality constraints, and so we're going to start to transition to kind of the what I think of as the second phase of the course, where we think of where we're solving optimization problems via algorithms instead. Okay. So this topic here called linear programming kind of gets us to that, and then after the midterm, we'll be working a lot more with MATLAB. Talking about how do we formulate an algorithm, how do we program it, and what that really looks like. Okay, so this is kind of like an in-between, kind of building up some kind of important concepts, but also kind of really being really useful itself. Okay. All right, so a few announcements, and so today I spent some time kind of looking ahead a couple weeks, and so if you look at the syllabus, the first midterm was actually going to be scheduled for Wednesday, October 4th. I don't think we'll make it there, and so I don't think we're going to finish everything with linear programming in time for that. So I am going to push back that midterm. So midterm 1 is going to be on Monday, October 9th instead. So basically the class after that. Okay. And so just kind of looking ahead in the schedule a little bit, we have homework 2. So homework 2 is out there right now. That is due next Thursday. Not Monday, October 4th, October 9th. Our class takes place on Tuesday, Thursday. So it'll be Tuesday, October 10th. That.
And that's what I was going to ask you. September 27th is a Wednesday.
Sorry about that. Okay, so midterm 1 is going to be, basically the class after that. Okay, so homework 2 is due next week, and then homework 3 would do a week after that. So that'll be actually October 10th, October 5th. Sorry. So homework 3 will be a fairly short homework, just because I'm only going to give you guys a week to do it, and so it'll be due on October 5th. Okay. And then midterm 1 pushed back until Tuesday, October 10th. Okay, so that's just to make sure we kind of finish enough content in linear programming, not only for you to do the homework, but also just enough to kind of be on the same. Okay. All right. I think that's all my announcements, and so definitely make note of that. I'm going to send an announcement after class today just to kind of confirm it. That the midterm is pushed back. And then homework 3 will probably be posted early next week. So I started working on the solutions today. I'll probably finish it up tomorrow and maybe Sunday or Monday, and then post it then. Okay. All right. And so, are there any questions about any of this before we get started for today? Okay. All right. So let's go ahead and get started. So the topic today is linear programming. So like I mentioned earlier today, we're just about done with all what I consider to be the classical methods of optimization. Okay. And so when optimization kind of first became a thing, when people first, started formulating the theory behind it, people used to solve optimization problems pretty much like we did before. Okay. But then once kind of computers started coming around and those started to become more powerful, people started looking at optimization in kind of a different way, in terms of, not really kind of a problem solving process that we do by hand, but really more as like an algorithm that we kind of design for a computer to do. Okay. And this is really important because, if you wanted to tackle kind of a more complex optimization problem with a lot more variables, that's really hard to do with the classical methods. And so the way that we describe it is we say that the classical methods don't scale well. And so when you start adding more design variables, when you get to 3 design variables, 4 design variables, it's not very uncommon in practice to have, design variables up to 20 or 30. Okay, those are practically impossible to do with the classical methods. Okay. And so we need another approach. We need a different way to approach these problems so that we can actually solve these in practice. Okay? And so with that said, for the rest of basically for the rest of the semester, what we're going to be doing is introducing different algorithms or different approaches to solving these problems. And we're starting with kind of the very kind of the simplest one that we can do, which is linear programming. And just like the name suggests, linear programming is designed to tackle problems with linear functions, so linear objective functions, linear constraints. Okay. And so what do I mean by linear? Right? And so that's kind of the key to these whole methods is kind of the class of problems that they work for. Okay. And so when I say linear, what I mean is that all of the variable terms, so all of the design variables, have an exponent of 1 in all of the equations. For example, let's say that we have the following objective function. So then we have a 3D objective function, so three design variables. And so a linear function would look something like this: a1x1 plus a2x2 plus a3x. Okay. And so if you look at all the x terms, so the x terms being our variables, they all have an exponent of 1. And so what we can say is that this equation here is linear. Okay. And I think people kind of get confused sometimes because when we talk about a function being linear, we're only really thinking about just the variable terms. And so the constants in front can be nonlinear terms as well. And so we could easily have something like e A over L times x1 plus, E squared square root of A L times x2 plus, maybe just E L x. Okay. Where E, A, and L are just constants. And so the coefficients in front of the x terms, those can be nonlinear. But as long as the x terms themselves, the design variables, as long as those have exponent 1, then our function here is still. What we can have is the x's when the x's have some exponent other than 1, that's not a linear function. So let's say, for example, we have a1 x1 squared. Okay, so this right here would not be linear. Because the x1 term has an exponent of 2, and so that would make it a quadratic term technically. A square root is not linear. So remember, technically a square root is an exponent of 1/2. And then anything in the denominator too, so any kind of reciprocal term as well. So if you have a3 over x3. So x, if the variable is in the denominator, technically it has a negative exponent, and so that would also not be. Right, so we're just looking purely at just linear functions, and so on the one hand, this seems like it could be pretty restricting, because as we know in engineering there are a lot of functions, a lot of equations where the design variables appear in a nonlinear form, and that's true. But for now we're going to just focus on just the linear equations, and you'll be surprised actually. So there are a lot of applications where we have just pure linear functions. And we can do things like kind of resource optimization, optimizing resources in different ways, maybe market research, things like that. Okay, so I have quite a few examples throughout these these next 3 or 4 lectures that kind of go. Okay, any questions on this so far? Okay. All right, but before we actually start solving problems under linear programming, there's actually quite a lot of context. So there's a lot of kind of prerequisite stuff we kind of have to go through. So I think the first thing we have to do is kind of remind ourselves, first of all, what is a linear system of equations and how do we actually go about solving? Okay. But first, let's talk about the standard form from a linear programming. And so sometimes you'll see me use the acronym LP for linear programming, just because linear programming is kind of a long thing to write down. Okay. All right. And so we're no stranger to the concept of standard forms, and so we've seen standard forms for all of our optimization problems so far. And so linear programming is not not any different. Okay. And so usually before you start an algorithm or before you start solving an optimization problem, usually it's best to put things in its standard form. Okay. So let's go over what that looks like for a linear programming problem. And so the first thing you'll notice is that by default, a linear programming problem assumes that you're running a minimization. Okay, you can do a maximization. It's just that you kind of have to adjust your objective function a certain way. Okay. Right, so we're minimizing the following function, and so this will be our objective function here. And so our objective function is going to be a function of all the design variables, and so we can have up to n. Okay. Remember, n is the number of design variables. Okay. We'll see over the next few weeks that or couple of weeks that we can actually increase n quite a bit. Okay, we were quite limited before to n is equal to 2 or 3, but with linear programming you could kind of scale it up much more easily. Okay, and so our objective function looks like the following, and so it has to be a linear function. Okay, so each of the design variables are linear, so they have exponent 1, and we're going to assume that there's a coefficient in front of each one, labeled by c. So we have c1x1 plus c2x2. Okay, and this trend continues all the way up until the end. And so we have cnxn. In addition to the objective function, we're also going to have equations for our constraints. Okay. And we're primarily going to be working with equality constraints first, but we'll talk about later about how to incorporate inequality constraints as well. Okay. And just like the objective function, our constraints are also going to be linear functions. Okay. We're going to have a slightly different form though, and you'll see that the coefficients have kind of two terms in front, two indices. First equation should be B1. Second equation is B2. Okay. And so just like the number of design variables, the number of constraints, we can scale up quite a bit as well. Okay. And so in this case, we assume that we have m number of constraints, where m is that number. And typically we have less constraints than design variables. If we had more constraints than design variables, our system would be over constrained and we wouldn't be able to solve it. And if m equals to m, remember what we talked about is that we'd have we wouldn't have an optimization problem. We'd have just a linear problem. Okay. And so we can have many constraints, but the number of constraints should always be less than the number of design variables. Okay. All right. And one other new thing that we're going to add here is that we're going to assume that all the design variables are going to be non-negative. Okay, so they're going to be greater than or equal to 0. We're going to have x1 greater than or equal to 0, x2 greater than 0, ... xn. Right, so this is the standard form. All linear functions but they have certain restrictions to them. And so since we do have all linear equations here, so our objective function is linear, our constraints are all linear, you know, this kind of this almost kind of begs it to be put in matrix form, okay? If we put this in matrix form, it makes the writing a little bit more compact. And so once again, we're going to have a minimize. So we're minimize going to be over all the design variables, where our objective function is of this form. Okay. And so another way to write kind of a linear equation that we had above is we can say that that's equal to the dot product between two vectors. So we have a c vector where the c vector contains all the coefficients of that equation, and x vector where the x vector is all of our design variables. Okay. In the same way, we can write our constraints in matrix form as well. And so we can say that our system here is subject to the following relationship: if A x is equal to B. Okay. This A matrix here is M by N. Okay. That means the number of rows of the A matrix is equal to M, which is the number of constraints, and the number of columns is N, which is the number of design variables. Okay. And then the way that we obtain the coefficients of that matrix is we just pluck the coefficients off from our constraints. Okay. So in that form, it's a little bit more compact, you know, especially, and so I write this form just because, you know, again, we're going to be transitioning into MATLAB code. And so one thing that MATLAB does very well or very conveniently is solving problems in terms of, like, you know, in terms of matrices and vectors. So putting your algorithms and putting your you know, equations in matrix form will actually make it translate a lot more easily to code. All right. Any questions on this so far? Okay. All right, so here's our standard form. And so, you know, for the most part, you know, all of the, or most of the examples that we're going to do are going to be in this form. But if you were to solve, if you need to solve an optimization problem that's not in standard form, there are some kind of basic things that we can do in order to get there. And so these are the things to do when you are not in standard form. And some of these we've gone over already, but I think it kind of bears repeating here just because they're, you know, fairly simple. Number one, I think, is the simplest one. And so, you know, the one, I think, kind of the most restricting thing that people find about linear programming is that you're restricted to minimization. Okay. If you have a problem where you want to maximize something instead, you can still use linear programming if you have a maximization problem. It's just that you have to take the negative of the objective function. So instead of saying that you want to maximize f of x vector, okay, what you're going to do instead, you're going to minimize, which is standard form, right? And so in order to get in standard form, we have to have a minimization problem. But instead of minimizing f of x, we minimize minus f of x. Very simple. And so if you have a maximization problem, you just multiply by negative 1. All right, 2. And so another big part of the standard form is that we assume that all the design variables are non-negative. Okay. If you have to have negative design variables, so let's say that you have a problem where negative values are permissible, you can still use linear programming. It's just that you would need 2 variables to to characterize. And so we're going to redefine the variable as a difference of 2 non-negative variables. So let's say that for a particular design variable, so let's say that you're designing something where it's okay to have certain variables be negative. Okay. And so instead of optimizing over x sub j, you're gonna optimize over xj prime minus xj double prime. Okay. Wherever you see x sub j in either your objective function or in your constraints, you just substitute with xj prime minus xj double. Okay. And so you have to be careful doing this. Is that this does increase the dimensionality. So instead of solving for 1 design variable, you need 2 design variables to come up with that 1 value. Okay. But again, because we're using a different method, scaling up by 1 is not as big a deal as it was before. All right. But that's not too common. And so I would say, having non-negative design variables is actually just fine in most cases, because most engineering parameters are non-negative by definition. All right, but this last one is probably the one you're going to use most commonly. Okay. And this is what to do if you have inequality constraints. And so in the standard form for a linear programming problem, we have to have linear constraints. Okay. But sometimes, just the problem that you're looking at just naturally has inequality constraints. You can convert inequality constraints to equality constraints by introducing something called the slack variable. And it's really kind of quite simple. So let's say that you have an inequality constraint like this. You have a1 x1 plus a2 x2 plus dot 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 an xn. So that's going to be equal to b1. Okay. So this still fit the criteria of being a linear function, except that it's inequality, and so technically it's not in standard form. And so to convert this, we can introduce a new variable, and we'll just call it y. We have a1 x1 plus a2 x2 plus dot 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 plus an xn. I'm going to add a new variable here. Call it y1. And then instead of being less than or equal to b1, we're just going to set it equal to b1. Okay. So this y1 term that I added here, this is our slack variable. In other words, it's a variable that kind of compensates for the fact that we may not be bound by the inequality constraint, and so that this kind of slack variable kind of gives us some slack there. Okay, and so just like the previous one, this does increase the dimensionality of our problem. And so this does mean you have an extra variable to solve for in your problem, but that's not going to be as big a deal. Okay. All right. So those are the three things that you can do. So if you have an optimization problem that's that at least has linear functions, okay, so that's the first thing you have to look at. And so if you do have a linear objective function and linear constraints, but it's not quite in standard form, these are the three things that you can do in order to get there. All right, so the next thing I have planned here is an example. So before we jump into that, are there any questions on this? Okay. All right, so let's do an example. And so this is not quite linear programming just yet. This is kind of more of like a visual kind of example, so you can kind of see what's going on. Okay. And so for this example, let's say that we work for a manufacturing firm, and so that they specialize in producing parts. Okay. And these two parts have very interesting names, so we'll call them part A and part B. Their names are redacted due to an NDA, okay, so I can't say what they are. But we do know, exactly how long it takes to make each part and how much profit they make. Okay. And so we can summarize that in a table. So this table, A, B, right? And so this first part of the table here is going to tell us, how long it takes to machine each part on each of the particular machines. So we have the lathe, we have the mill, and the grinder. Okay. And so the typical process to make part A requires 10 minutes on the lathe, on average, 4 minutes on the mill, and 1 minute on the grinder. Okay. So a total of 15 minutes, but those 15 minutes are kind of split in between the three machines, just like that. Okay. Whereas for part B requires 5 minutes on the lathe, 10 minutes on the mill, and 1.5 minutes. Okay, not necessarily in that order, but we're talking kind of total time. And so kind of further complicating our problem here is that each of these machines has a maximum amount of time that you can use it per week. And this is kind of just due to just kind of the availability of the labor, maybe the availability of the machine, maybe they just have to cool down and stuff, but there's a cap on how much we can use the lathe, the mill, and the grinder. Okay. And so for the lathe, let's say that we can only use it for 2,500 minutes a week. Okay. The mill can only be used for 2,000 minutes a week. And the grinder can be used for 450 minutes. And then finally, we have the profit from each part. Okay. And so each part A that the company sells is worth $50. And then each part B that they sell is worth $100. Okay. So that's kind of the information for the problem. And so what we want to find is we want to find the optimal number of each part to make. And so the optimal number of part A's, the optimal number of part B's to maximize the profit for the company on a per week basis. Okay. So we'll call the number of part A's, we'll call it X sub A. Part B, we'll call X sub B. And then what we want to do is we want to maximize the profit. Okay. Okay. So this problem right here actually lends itself very well to linear programming. So once we actually start formulating the constraints and we start formulating the objective function, we'll see that everything is linear. But before we start solving this, are there just any questions on the setup for the problem? Yes. Oh, sorry. Okay. All right. So we're given these this data, but we don't have any equations yet. So let's go ahead and formulate our constraints and our objective function. Okay, so let's start with the constraints. And so we know that the amount of time that we can use each machine is going to be constraining our problem here. Okay, so let's start with the lathe. And so the lathe we can use for a maximum of 2,500 minutes. Okay. And if each of part A takes 10 minutes, and so we take 10 times X sub A, and each part B takes 5 minutes, do 5 times XB, okay? That has to be less than 2,500, because that's the total amount of lathe time that they have each. Okay. All right, so we can form similar equations for the others, and so we have 4. So I'm going to do the equation for the mill now. So 4XA plus 10XB has to be less than or equal to 2,000. Okay. And then finally for the grinder, so for the grinder, we have XA plus 1.5 XB less than or equal to. Okay. So notice that all of these are inequality constraints, right? Because there's no requirement or the problem didn't specify that we have to use the lathe for $2,500 or 2,500 minutes per week. It just has to be less than that, okay? So that's why there's all these less than or equal constraints. And so to put this in standard form, we have to include additional variables. And so to each of these equations, I'm going to add a slack variable. And so to equation one, I'll just add y1. For equation two, we'll call it y2. For equation three, we'll call it y. Okay. And then by doing that, we can change these less than or equal to signs to this equal signs. And so you can see here that by adding those slack variables, we've kind of more than doubled the dimensionality of our problem. So instead of two design variables now, we have three. I mean 2 plus 5, 2 plus 3, which is 5. I need to sleep. Don't worry, we're not actually going to solve this problem. But, I'm partially kind of bringing this example up just to kind of give us practice into putting in standard form, and then we're going to more kind of visualize and see kind of what's how the problem's going to go along. Okay. Next, we have our objective function, and so our objective function basically says that we want to maximize our profit, right? And so let's maximize. Right, and so we know that we make $50 off of each of part A, so we have F of XA, XB equal to 50 XA. And we know that we make $100 off of each of part B that we sell, so plus 100 X. All right, but of course, this is not standard form. And so remember, standard form has us put this in the minimize. Okay. So instead of a maximize problem, we need a minimization problem. Okay. So we're going to minimize f of XA and XB, and we're just going to multiply everything by -1. So we go minus 50 XA minus 100 X. Okay. So that would be kind of the standard form that we would work. Okay. And so everything in purple is how we would typically solve it. Okay. We haven't actually learned how to solve these problems yet, but we can at least kind of see, visual, at least kind of see how we would put this in standard form. All right, any questions on this? Okay. Okay, but to solve this problem, we're kind of in luck because even though we technically have 5 design variables with the slack variables, we can actually solve this visually, kind of using our methods that we learned kind of very early in the class. Okay. And I'm bringing this up just because, you know, when you have a linear programming problem, because the functions are linear, there's only a few conclusions that you can draw from this. And so, in other words, you know, the result of a linear programming problem basically only has there's basically only 5 things that can happen. And so we're going to use kind of this visual to kind of show what those 5 are, and then kind of use the figure to kind of back up what that. Okay. So let me go ahead and draw our plane here. So we have a 2D, basically a 2D optimization. Okay, so I'm going to assign XA to the horizontal axis and XB to the vertical axis. Okay. So first thing I want to do is let's plot out our feasible region. And so I'm going to take the 3 constraints that we have. I'm going to put them in a form where we can actually plot them, and then actually plot them on the plot. Okay, so our first constraint was 10xa plus 5xb less than or equal to 2500. Okay. And so to plot this, we have to get this to a form of xb is equal to something else. Okay. So I'm going to subtract xa from both sides and divide by 5. If we do that, we get xb is less than or equal to 500 minus 2xa. Okay. And so if we plot that function, it looks something like this. So we have a y-intercept of 500, and it would decay. So this right here, this would be constraint. Okay, second constraint. So second constraint that we have is 4xa plus 10xe. So that's going to be equal to 2000. And so same thing here, we're going to solve this equation for xb. I'm going to subtract 4xa from both sides and divide by 10. And so this gives us xb is less than or equal to 200 minus 2/5 xa. Okay. Let's go ahead and plot that. And so that would be 200, maybe probably somewhere around here. Then we have a slope of minus 2/5. But this right here would be constraint 2. And our third constraint is xa plus 1.5 plus b less than or equal to 450. Okay. Once again, we're going to solve for xb. We get xb is less than or equal to 300 minus 2/3 xa. So that would look probably something like this. We have 3 kind of linear lines, and that's expected, right? And so, you know, when you have a linear programming problem, you know, everything should be linear. Okay. Okay. And so the feasible region is just whatever region is underneath all of these curves. Okay. And so you can see here that, you know, we only have kind of a smaller, relatively small area. And so the feasible region is just this one right here, okay? We can't do anything above that line because that would be, you know, kind of violating constraint 2. And so the only feasible region is just that one.
Sometimes a constraint may not be.
Exactly, right. And so in this case, constraint 3 is not even, you know, it's not binding the solution at all because, you know, it's being constrained by constraint 1 and 2. And so in this will be a case where we kind of ignore constraint 3. Okay. So that's good. So we have our feasible region. So now what we're going to do is we're going to plot our objective surfaces. Okay. So let me write our objective function here just one more time. And, you know, just for the sake of simplicity, just to kind of save myself a bit of writing, I'm going to use the maximized version. Okay. So there's 50xa plus 100xb. Okay. And then just like before, or just like we did with all the constraints, we're going to solve this expression for xb. Okay. And so we solve it for xb, we get xb is equal to minus 1/2 xa plus f of xa x. Okay. So that's good. Okay. And so what we can do from here, if you recall from the first homework, is that, you know, now that we have this kind of expression for the objective surfaces, we can plug in different values for f, and that's going to give us a family of curves that we can plot in this plane. And what's interesting about this is that, you know, because our objective function here is linear, all of these curves here are going to be perfectly parallel to each other because they're going to have the same slope, but just different y-intercepts. Okay. Right, so let me plot some here just so that you can see. And remember what that f represents. So that f represents our total profit, and so, you know, we're going to be plugging in basically different you know, profit values. Okay, so let me kind of clean this curve up a little bit. So I'm going to erase kind of these tooltips for constraints 1, 2, and 3, just to kind of give myself a little bit more room to draw these. All right. So let's say that we want to see, is it possible for us to make a profit of 30,000 from selling these parts? Okay. And so we plug in f is equal to 30,000. You know, we kind of plug it in, you know, and maybe we get a curve that looks like this. This is our curve for f is equal to 30. All right. So that would be great. That would be great if we can make a profit of 30,000, but you can see that that's not possible. And so, you know, we don't have any intersection between this curve and our feasible region. And so we can say that there's no viable solution on this curve. So let's reduce this. And so let's plug in f is equal to 25,000 and plug that in. So this is f is equal to 25,000. So you can see the curve for f is equal to 25,000 is parallel, but not quite in the feasible region yet. But we are getting closer. So let's say that we continue, not quite 20,000. So let's say this is 22,500. Okay. So still parallel to the last curve, but still not quite there. Okay. And let's say if we reduce it even more, so let's say that if we reduce f to 20,000, for the first time we're able to get some feasible solutions, right? And so it is possible for us to make $20,000 in profit as long as we pick anything on that curve. Okay. But with that said, just judging on the trajectory of these lines, right? So we know that, just based on the direction of these lines, we know that they're kind of going this way, right? And so that tells us that if we can move this curve up a little bit more, we can probably maximize our profits a bit more. Okay. And so let's go ahead and do that. So if just by trial and error, and this would normally be very hard to obtain through trial and error. But let's say that we got a curve that looked like this, not quite like that.
So just find the intercept between interest rate 1 and 2.
Well, I mean, now that you've kind of plotted it out, you know that point is kind of where the optimum is, but you kind of have to plot a few of them to know kind of which direction it's going. So it's
We're only doing like a handful.
yeah,
Mhm.
exactly, yeah. Okay, so this purple line that I drew here for this particular problem has a profit of 21,875. Okay, and you can see that it kind of just barely kind of kisses that feasible region. So we kind of just have one intercept between the feasible region and the objective curves. Okay, and so that 21,875 is our optimal profit. And so in this particular problem, we have one optimal solution, and that one optimal solution occurs at that one intersect point. Okay. All right. And so we've solved this linear programming problem using visuals. Okay. And so the visual way works well when you have two design variables, but of course, when you kind of scale it up to 3D, 4D, 5D, then this isn't available. But I at least wanted to bring up this 2D case just because we're going to highlight kind of a few more features of this solution. Okay. Okay. But are there any other questions on this example here so far? Okay. All right, so like I mentioned, the way this problem is written, we have one optimal solution, right? That's one possibility of a linear programming problem, and in fact, it's the best possibility when you have just one optimal point. So these are the possible results. There's 5 of them. You can have one optimal solution, which is the best. Okay, and probably the most common. And most common you'll find just one optimal solution, which is good. Okay. Another possibility from a linear programming problem is that you might have infinite solutions. Okay. And so visually, that might look something like this. So I'm going to draw just kind of a slightly modified version of the curve above. Okay. So let's say we have a situation where our feasible region looks like this. And let's say that our objective curves, and so these are the curves that we find by formulating our objective function, is parallel to this top edge right here. So exactly, so it's going to look like this. So each of these blue lines that I've drawn here are the objective curve for different values for f. Okay. And then if it's perfectly parallel to the feasible region, or one edge of the feasible region, you may get something like this, where maybe this curve right here is the optimal f. Okay. And so based on our problem, that's the best we can do for the objective function. But instead of intersecting the feasible region at a single point, we're intersecting the feasible region on an entire edge. And so technically, any design point on that edge would be a feasible optimal solution. We can choose a point here, we can choose a point here, okay? Technically, we can choose any point on that line. So what we say is that we have an infinite amount of optimal solutions, okay? All right. So this usually only happens in linear programming just because, we're limited to just linear functions. And so everything is online. And so to have, to have your objective function basically parallel to one of your constraints, is a lot more possible here than it is in typical nonlinear optimization. Okay, so that is another thing that can happen. Okay. Okay. Another thing that can happen is that you may have a situation where you have an unbounded solution. And so this usually occurs when your feasible region also is unbounded, right? Because if you look at the feasible region for this one and also for the example that we did, you can see that it's bounded by the coordinate axis. Okay. And so yes, we know that the feasible region has to be below our constraints, but we also know from beforehand that our design variables have to be positive, right? And so the coordinate axes kind of form another kind of natural barrier for the for the design variables. Okay. But you may have situations, that may look like this. So maybe you have a feasible region that looks more like this. So maybe your feasible region is kind of this unbounded region up here. Okay. Or technically, this kind of continues on to infinity. And so what can happen in this case is that, you can draw your objective curves. Okay, so maybe your objective curves look like this. Okay. But maybe the more optimal value for the objective curves is upwards. Okay. And so in these cases, you can kind of almost infinitely keep improving the objective function and still be within the feasible region. You may have a result that's unbound. This is not very common. So this usually means that the optimization problem was kind of ill-posed or not really described well. But mathematically, technically, it is possible, and there are some kind of niche situations where it happens. Okay. Okay. The fourth possibility for a linear programming problem is maybe there's no overlap between the feasible region and the objective functions. In those situations, we say we have no solution. Not going to draw that one just because that one's kind of more self-explanatory. And the last possibility, the last possible result from a linear programming problem is that we have one trivial solution. Okay. So this also is very rare, and it usually means that your optimization was kind of ill-posed. And this only happens when the number of constraints equals the number of design variables. So those are your 5 possible outcomes. So you either have one optimal solution, you have infinite optimal solutions, you have an unbounded system, you have no solution, or you have one trivial solution. Okay. All right, and then as we kind of go, through the algorithms next week, you'll kind of see mathematically how each one of these looks like in terms of the equation. Okay. But the first thing I want to do is just kind of remind you kind of the visual way to do optimization and kind of how to visualize each of these techniques. All right, any questions on this? Okay. All right, so the last thing I want to cover today for the last 6 or 7 minutes is to kind of review systems of linear equations. So now that we finish kind of the intuition and kind of the background of kind of linear programming and kind of what they look like and what they can result, what can result from them, you know, we're going to start to get into the details of how to actually solve these things. Okay. And before we do that, we kind of have to remind ourselves a little bit of how to work with these systems of linear equations. Okay. In particular, we're going to review a technique called pivoting. Okay. And so when we say that we're going to pivot on a linear system, we're going to perform algebraic operations to eliminate variables one at a time. And so remember, for a system of linear equations, you have a certain number of equations, a certain number of unknowns. And the objective is to solve for the values of each of the unknowns, right? One way that we can do that is to kind of systematically eliminate each each variable until we get one equation and one unknown. And then we go back and kind of back solve for all the other things. Okay. So I'm hoping, you know, you guys are familiar with this concept, or at least you've seen it before. So I'm just going to kind of jump into an example. You know, of course, we're not going to finish this example today, but you know, I at least want to do the first step just to kind of plant the seed of the idea in your head, and then we'll kind of expand on it on Tuesday. Okay, and so what we want to do is we want to use pivot operations to solve the system of equations. We have 2x1, 3x2, 2x3, 1, x1, x2, x3, 6, x1 minus x2, x3. Okay. Okay, so we have a 3 equation system. So 3 equations, 3 unknowns. Okay. And what we want to do is we want to solve these equations for the values of x1, x2, x3 that satisfy the system of equations. All right, and so you know, you guys have probably seen systems of linear equations before. We've seen them in this class before. Okay, so everyone kind of has their own favorite way to solve these, but because of the way the linear programming algorithm works, you know, I'm going to solve this in kind of a very kind of specific way. I would say, you know, it's not the most efficient way, and so I think probably some of you might be kind of annoyed how slow this is going. But this is kind of important for us, you know, to kind of build on next weekend. Okay. Okay, so remember, we're going to solve this by pivoting. And so by pivoting, we're gonna solve one equation for one variable and then plug that into the others to eliminate it. Okay. Okay. And so just a little bit of terminology. So when we say we pivot around a variable, we're going to try to eliminate that from the okay. So let's pivot around x1. And so our goal is to try to eliminate x1 from our equations. Okay. So let's take the first equation. And we're going to solve it for x1. First equation here is 2x1 plus 3x2 plus 2x3 equals 1. Okay. And so to solve this equation for x1, I'm going to move all the x2, x3 terms to the other side and divide by 2. x1 is equal to 1/2 3/2 x2 plus x3. Okay. Good. And then what we're going to do from here is we're going to plug this into equations 2 and 3. Okay. And then what we're going to get from that is that x1 is going to be eliminated from those two equations. Okay. And then from there we'll have a system of 2 equations and 2 unknowns that we can solve for x2 and x3. Okay. And we're going to kind of do this systematically until we get the values for x1, x2, and x3. All right. Any questions on this before we wrap it up for today? Okay, all right, so that's all we got time for. So we'll continue this example on Tuesday. So thank you everyone for coming today. Hope you enjoy the rest of your day. Hope you guys have a good weekend, and I will see you guys on Tuesday.
Have a good afternoon, Professor.
Okay.
Hey, so I do that, keep getting the wrong answer. Like finally, one time I did it and I finally got the right answer here. But so this way I tried the Lagrange theory, right?
Yep.
I got like 48, 46, and I was doing it the other way. And what I would do was that I would take your string, solve for x, right, and get that there.
Yep.
And what I think I was doing before was I would plug this into equation 2.
Yeah.
And that would give me like y equals 31/35.
Okay.
Which then when I solve it out, x becomes like some random number. And I know that wasn't the right answer, but if I plug it into equation 1, I get the 40.
Okay. I see.
And then if I plug this back into equation 2, I get some weird number. But if I plug it back into this one, I get, or if I solve for y, I get 20, and then
Right.
yeah, I would get 40. So that is the right way to do it. How do I know which one to plug it? Like once I get this,
Yeah.
how do I know where to plug that one into?
So this is the constraint right there. I wonder if this problem is ill-posed. I wonder if it has multiple solutions because it's. I didn't check it, so I mean this is the way I kind of solved it. For me.
Okay.
I kind of I solved it and then plugged it back in and solved it that way. But there might, I wonder if there's multiple complement. That's
Well, I didn't check if the other ones were like maximums or minimums, but
I mean that
is that what I need to do?
that's yeah, technically what you although I didn't do that for this one. This one I just kind of took the first one. That's probably it, is that, there's probably multiple optimums, and then some might be saddle points and some might be
Oh, okay.
like maximums.
So I just need to check each one and make sure.
Yeah.
There wouldn't be a time where there'd be like two maximums, right?
There could be. And so that's the weakness of the classical method, is that we're basically just looking at places where the slope is 0.
Okay, so there could be two.
Exactly. Yeah. So there might be two humps
Okay.
like that. And so that's kind of the weak. And so that might be what's happening here, is that these might both be maximum, and there might be like,
Oh, okay.
yeah, or it's in 2D. So it's like a hill and another hill.
Oh, okay.
Yeah.
How would I be able to determine which one is, I guess, more often?
You just plug it in. And so whichever one, so you take these two, you plug it in up here, right?
Mhm.
And then you get a value for
Oh,
F.
for F, and then that would, whichever one, I guess, if you're trying to maximize or minimize would be.
Exactly. Yeah.
Oh, okay.
Yeah, but that is a weakness of this method, and so, people think, mathematically it's more sound, but then, you're not really doing a global search, you're just kind of searching.
Okay.
And then once we get into the MATLAB stuff after the midterm, we'll learn how to do more of a global search. We'll find a global.
Okay. Then another question too, like, let's say you have if you have a equation, right, and you have maybe a hump here, but then it goes up, and then you have a constraint that cuts it off, but that point's higher.
Yeah.
Even though that's 0, how do we know that it would still be a solution, but you wouldn't find it using the derivative?
Exactly, yeah, you wouldn't, and that would be another weakness of this method
Oh,
too.
okay.
So that's why we're kind of getting into this stuff. So what you'll see is that linear programming, we'll be able to search on those boundaries a lot better. And in fact, for linear programming, like you'll see that the optimal solution is at least on at least one of the boundaries, because we're looking at all linear functions. So there's no hump. It's impossible to get a hump with a linear function, and so we have to kind of search on. the
Oh,
boundary like
yeah,
that.
okay.
And yeah, so that's, there's a lot of weaknesses. That's why no one really does this. It's mostly just for
Okay.
kind of just concept, when you're first kind of introduced to optimization. But yeah,
Okay,
everyone uses kind of this stuff.
so it's just the baby step. and it's
Exactly,
not really- okay.
exactly, yeah. There's a lot of issues with this, but it's just for introducing, what are design variables, what are constraints, what are objective functions.
Okay. Yeah, I guess, yeah, that cleared it up now.
Yeah. It's a little dissatisfying now, but then it'll get better.
Okay. Yeah, because this is, I'm like, why am I getting all these different answers?
Uh-huh.
Well, I finally got the right one today, but
Uh-huh.
like, yeah, for a couple days, I was just like, I kept doing it over and over again, kept getting the wrong answer. And I'm like, and it's funny because I did the other ones, I did B and I got the right answer, and I did some of the other ones, I'm like, I'm doing the same thing.
Uh-huh. Yeah, it's there's
Okay, so
it's a lot of-
depending on where you plug these into, it actually
Yeah.
makes a difference.
Yeah, I should have checked. I should have checked to see if there are multiple optima for this one. So, but usually if you have just a quadratic function, then it's usually just one optimum. But I wonder if it's because the cross term kind of made a saddle point or something.
Okay.
That's usually what happens. But yeah, usually if it's quadratic, there's usually only one.
Yeah,
But yeah, I'll check it again and see.
okay. I think that's it for now. All right, well, thank you, Professor.
Yeah, no problem.
Have a good rest of your day.
You too.